So in the first video in our series on learning HVAC diagnostics when you're kind of on your own without a mentor, we touched a little bit on the basic structure of a circuit and how they work. What we're going to do in this one is we're going to kind of carry on a little bit and go into the difference between series and parallel wiring, because as a technician, you're going to be working over a span of decades of equipment, and a lot of the older stuff, there's a lot of what's called in-series wiring, where the newer stuff is leaning pretty heavy towards parallel wiring. So knowing the difference between two really helps out. And in the process, we're going to start bringing in schematics. We're going to start introducing that as we learn about the wiring diagrams and things of that nature. And we're also going to start bringing in using multimeters and sequence of operations as we continue focusing on these little subjects and go along. We're going to start bringing all those other features in so that we can kind of blend it all together and get a big picture view on how to actually start diagnosing equipment. So let's get started on a difference between series and parallel. So here we have two real-world examples of a series and parallel circuit. On the left side, we have a series circuit that is pretty typical of a central air conditioning system's low voltage control circuit. So over here we have a transformer that is in the air handler. It takes 120 or 230, converts it down to 24 volts for our control voltage. It is sent from our R terminal on the control board in our air handler to the R terminal on our thermostat. When the thermostat calls for cooling, it closes a switch between R and Y. From that Y terminal, it goes to the Y terminal on the air handler, which is like a junction point. And from that Y terminal on the air handler, it goes out to our outdoor condensing unit. Now, in a lot of units, you'll have a low pressure switch, which is a switch that is on the suction piping of your refrigerant. You'll have a high pressure switch, which is a pressure switch on the liquid line of the refrigerant. And then this here is our symbol for our contactor, that little resistor symbol. And once it goes through the contactor pulls in, allows power to go to our condenser fan motor and compressor, which starts the outdoor unit. And then it makes its way back up to the common terminal on the control board in our air handler, which eventually makes its way back to the common on the transformer. So we have a full circuit going all the way around through all these components. Now, a series circuit, you'll notice, has no other path than through each component one at a time in order. It can't do anything else. So if any one of these switches are open, the whole entire circuit is dead. So let's go ahead and close the switch on our thermostat like we're simulating a call for cooling here. And you can see we have power flowing, our contactor closes, our system is running, everything's good. Now, if we have a low pressure situation on our refrigerant and that switch opens the circuit, you can see the whole circuit dies. So our whole entire cooling system shuts down. Same thing for the high pressure switch. If that opens, whole circuit dies. Now on the right side, you see parallel wiring, and this is something you're always going to see in situations like with zone valves on hydronic boilers. So you can see we have each one of our thermostats, individual zones. Each thermostat has its own zone valve motor. Now in a parallel circuit, we have the transformer here, that's the 24 volts, and it sends power up to each thermostat. So whenever you look at zone valve wiring, you will notice a wire coming off the 24 volt side of the transformer, and they all bundle together with a bunch of wires, and each one of those wires will go up to our thermostats. Now on the opposite side, on the zone valve motors, you will see wires coming off of each one of those zone valves all tied together to another wire that goes all the way back to common on our transformer. And so what this setup allows us to do, as we discussed in our first video, if you have a path from your power source through the components in a circuit and going back to your power source again, you have a complete circuit. So as you can see the way this is wired, if I were to activate this thermostat, we have that path from our power source all the way around. And each one of these zones have that ability. If I were to close this thermostat, we have the same thing there. If I open this one, it doesn't affect that one, because each one of these thermostat zone valve circuits here have that ability to run from the power source through the circuit and back to the power source again. So each one of these zones can act completely independently as they wish without affecting the other in any combination. All right, so what I want to do now is we're going to go back to the cooling circuit. That's our series circuit. I'm going to show you how to use the schematic a multimeter, the sequence of operations, and a comprehension of how the circuit is structured and how to use all those things together to pinpoint an exact problem in the system. So what we're looking at here is an open high pressure switch, but we don't know that, right? We're just walking up on the unit. We have no clue what's going on. Now, when you look at this schematic, you can see it's all wired in series, and when components are wired in series like this, what do you have? You have a sequence, right? At first for the transformer, then the R terminal to air handler, R terminal thermostat, Y terminal thermostat, and so on. So what we can do now is we can take our multimeter and we can pick a middle point, go straight to the thermostat, and we can take our multimeter and see if we have 24 volts at that Y terminal. Because even if that high pressure switch is open, we still have a path from the Y terminal on the thermostat all the way back to the transformer. So we should still have 24 volts there so long as the thermostat's calling for cooling. Now, when you're testing terminals on a thermostat, just as a side note here, if you don't have a common wire hooked up to the C terminal, you can't use the C terminal to try to get a reading off a Y. With your multimeter. So what you can do is that you can either go from R to Y, in which case if you have a closed switch, which is what you want to see in cooling mode, you should read 0 volts. Now if you want to use a wire more like a common, you can use any other wire that's not being used right now. So if we're in cooling mode and you have a W wire hooked up, that wire is not being used, and that wire will act like a common wire because it's not part of a circuit right now. So you can go to Y to W, and if you have your thermostat in cooling mode and that switch is closed, you should read 24 volts on Y. Now, if we have 24 volts on Y, what's next in the sequence is the Y terminal off the air handler. So we can go up to the air handler, check and see if we got 24 volts on the Y terminal there. Now you can go from Y to C on the air handler control board, whether there's a wire hooked up to it or not, because that C is always hooked up back to the transformer, so it'll always work. So we have 24 volts there as well. So what does that do? That brings us out to the condensing unit. Now, the high and low pressure switches, they're buried deep in the condensing unit. We'd have to start taking it apart to get to them, but the contactor is very easy to get to. So we can just test and see if we have 24 volts at our contactor, and we don't. So what does that tell us? Well, in between the Y terminal and the air handler and the contactor are the low pressure switches. So guess what? It's time to hook up our gauges and see what's going on with those pressures. And this is how you can use all these components of schematics, understanding the circuit, using your multimeter and so forth to pinpoint problems in the system.